With each captivating image captured by the James Webb Space Telescope, it continues to receive attention from various corners of the cosmos, including planets within our own solar system. A year ago, we marveled at our initial glimpse of images showcasing the Carina Nebula, Stephan's Quintet, and notably, the mesmerizing Deep Field image. This particular image seemingly portrays numerous galaxies stretching into the vast expanse of the universe. Living up to the anticipation generated, the James Webb Space Telescope hasn't ceased to amaze. It has recently unearthed objects challenging established cosmological concepts. These enigmatic findings are now labeled as universe breakers by astronomers, perplexing the scientific community with their ability to contradict existing ideas. The reasons behind these discoveries remain shrouded in mystery, throwing our predictions and hypotheses into disarray. So what's the latest scoop from the James Webb Telescope? What groundbreaking information has it uncovered that was previously unknown to us? Join us as we delve into the revelations of how the James Webb Telescope has presented evidence suggesting the existence of another universe, challenging the conventional understanding of the Big Bang. Our universe, as we comprehended, emerged from a hotter, denser, and more uniform past, a concept known as the Hot Big Bang. This theory, a major scientific milestone over the past century, found shocking validation in the mid-1960s with the discovery of the cosmic microwave background, a remnant from the early hot and dense state. Over the years, the Big Bang has stood as the dominant hypothesis explaining our cosmic origins. However, fresh and critical observations have led astronomers and astrophysicists to consistently question both cosmic inflation and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, emphasizing the enduring nature of the Big Bang hypothesis. Assuming a traditional perspective, the portrayal of the universe's origin involves a smaller, denser universe in the distant past. The presence of radiation, such as photons, indicates that the universe was hotter at its inception and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels reach a point where a singularity could be formed, and the conventional laws of physics break down. Physics encounters its limits at the Planck time, approximately 10 to the power of 43 seconds, where extremely small distances, short durations, and high energy scales defy our understanding. Rewinding the cosmic clock to the theoretical zero at the beginning, a complex historical transition would be anticipated. If the universe started as hot and dense, then expanded and cooled, in this scenario, copious amounts of particles and antiparticles would have been generated, with surplus particles annihilated by radiation as temperatures dropped. The collapse of electroweak and Higgs symmetries gives rise to four fundamental forces and particles with non-zero rest masses. As the universe cools further, atoms like protons and neutrons form from composite particles called quarks and gluons. The fusion of protons and neutrons results in the creation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Ovid zones experience expansion due to radiation pressure, followed by gravitational growth leading to rhythmic scale-dependent impressions. About 38,000 years after the Big Bang, the universe cools sufficiently for stable neutral atoms to form, marking a crucial step where photons disperse with wavelengths increasing as the universe expands. The discovery of the cosmic microwave background over 5 decades ago solidified the Big Bang theory as the most supported explanation for the universe's creation. While most astronomers and astrophysicists embraced the Big Bang, steadfast proponents of the steady-state theory, like Fred Hoyle, persisted in defending increasingly implausible claims, only to face failure in light of overwhelming evidence. The evidence presented was unequivocal: it wasn't fading starlight, nor was it reflected or radiating heat from dust. Every conceivable explanation fell short. The cosmic afterglow spectrum exhibited a remarkable uniformity in all directions, resembling a perfect black body, yet it lacked correlation with the known contents of the universe. Despite this, Hoyle and his adherents persisted in obstructing scientific progress by advocating scientifically untenable alternatives. Even as the scientific community gravitated towards the Big Bang as the consensus, ultimately, scientific advancement prevailed, and the detractors lost traction, their flawed endeavors faded into obscurity. Meanwhile, the fields of astronomy and astrophysics experienced unprecedented growth from the 1960s through the 2000s, with cosmology witnessing particularly remarkable expansion during this period. We mapped out the vast cosmic web and delineated the universe's structure on a grand scale. We delved into the formation, evolution, and dynamic interplay of galaxies and their stellar populations. Yet, despite these strides, we encountered phenomena that defied explanation within the framework of the Big Bang. Observations revealed discrepancies that challenged the predictive power of the Big Bang theory. Notably, no exotic remnants predicted by the theory, such as magnetic monopoles or particles from grand unification, have been observed. The universe we perceive today seems to necessitate forces beyond our current comprehension. Yet, these remain elusive. At its inception, the universe required a precise expansion rate to balance the total energy density, a feat that the Big Bang theory struggles to justify achieving. Thal equilibrium or sufficient time for energy exchange across disparate regions of space presents further challenges. Given the vastness of the universe and its growth over time, these discrepancies pose significant challenges for cosmology and the scientific community at large. When theories fail to account for observed phenomena, two paths emerge: either refine existing theories or entertain alternative explanations. Cosmic inflation emerged as the most promising theoretical framework for extending the Big Bang paradigm. Inflation proposes an early phase of exponential expansion, flattening the universe and endowing it with uniform properties. It resolves the graceful exit problem and predicts the emergence of quantum fluctuations, which manifest as density and temperature variations. Notably, inflation's predictions align with observed structures and variations, bolstering its credibility. While alternatives exist, none rival inflation's explanatory power. Despite earlier contributions to general relativity and singularities, Roger Penrose's work, including his collaboration with Stephen Hawking, failed to rival the success of inflation theory in explaining the universe's early moments. In recent years, there has been a concerted effort to undermine the credibility of inflation theory, advocating instead for conformal cyclic cosmology, which is inherently flawed from a scientific perspective. The primary distinction lies in their predictions. Conformal cyclic cosmology posits remnants from a universe preceding the Big Bang in the cosmic microwave background and the large-scale structure of the universe. In contrast, inflation theory dictates that the point at which inflation ceases and a hot Big Bang ensues must be causally disconnected from any such pre-Big Bang region. Every facet of our cosmos exhibits unique characteristics, and thus, we must trust in the universe to reveal what is true versus mere theory. Despite initial amazement, astronomers soon detected anomalies in the photographs transmitted by the James Webb Space Telescope. Since 2022, these revelations may necessitate a re-evaluation of crucial aspects of the universe's origins and evolution. One significant discovery made by the Webb telescope was the existence of fully formed galaxies much earlier than predicted by the standard model of cosmology. This discrepancy challenges the established sequence of events post-Big Bang, where stars and black holes form first, followed by the formation of galaxies. Such findings disrupt our understanding, akin to encountering grandparents depicted as children in a story. Furthermore, recent evidence has unveiled contradictions within science's fundamental theories about the universe. For instance, the discrepancy in determining the Hubble constant persists despite advancements in data precision and collection methods. Moreover, new data from the Webb spacecraft exacerbates existing challenges to the current cosmological model. These issues underscore flaws within the model itself, prompting suspicions among astronomers and physicists. While the model has undergone revisions over the past half-century to align with emerging data, some argue that these adjustments have been overly convenient. As a result, there's growing recognition that a paradigm shift may be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human intellect, emerged from Edwin Hubble's groundbreaking discovery of the expanding cosmos in the 1920s. Subsequent findings, such as the cosmic microwave background radiation in 1964, corroborated the Big Bang theory, depicting the early universe as a dense, hot soup of subatomic particles gradually cooling over time. However, achieving the current level of precision in cosmological understanding has required speculative extrapolation beyond empirical data. Cosmic inflation, proposed in 1981, was introduced to resolve inconsistencies in earlier Big Bang hypotheses, further highlighting the dynamic nature of cosmological theory evolution. According to this theory, the early cosmos experienced rapid exponential growth for a brief period following the Big Bang. While some problems are resolved by this idea, new challenges arise, especially considering the prevailing belief in the existence of not just one universe, but an infinite number of them potentially beyond our observational reach. Certain observable phenomena, such as hyperdense singularities within black holes, find support through indirect evidence. However, the contradictory findings of the Webb Space Telescope regarding the birth of galaxies and the persisting issue with the Hubble constant raise concerns. We may be approaching a tipping point where a significant overhaul of our current cosmological model becomes imperative, possibly requiring a re-evaluation of the fundamental building blocks of the cosmos, including time and space themselves. Cosmology, unlike many other scientific fields, deals with all-encompassing questions about the universe, its origins, and the role of observers within it. The study of consciousness and quantum physics touches on comparable themes as cosmology delves into the intersection of philosophy and science, grappling with fundamental assumptions that underpin our understanding. Challenging assumptions, such as the constancy of scientific laws throughout history, has been proposed by philosophers like Roberto Mangabeira Unger and physicist Lee Smolin. The idea that physical principles can evolve and change across time challenges conventional thinking. Physicist John Wheeler even suggests that every observation can influence the cosmos's future and past, radically rethinking scientific practices and questioning these fundamental assumptions is a significant leap. Considering the influence of theoretical assumptions on data collection, however, history has shown that revolutions in scientific thought, such as heliocentrism, evolution, and relativity, have led to profound shifts in cultural perspectives. A similar impact on our self-awareness might be anticipated from any forthcoming scientific revolution in cosmology. Philosopher Robert C. Trice argues that philosophy becomes necessary when additional scientific investigation fails to provide a satisfactory answer to a scientific topic. The ongoing debate revolves around whether philosophy is required to address the cosmological issues at hand. If fine-tuning existing models proves insufficient, a complete overhaul of our understanding of the universe may be necessary, accompanied by new narratives to communicate these paradigm shifts. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.